Hello everyone, how are you all? In the previous episodes, we looked at why analytical workloads are different from transactional workloads, why columnar storage matters, and how Exasol scales through massively parallel processing and shared nothing architecture. So at this point, the data is already been distributed across multiple nodes in this cluster. So what is the next obvious question? Where is the data is getting actually processed? The answer is in each node's main memory. So in this episode, we will look how Exasol uses main memory and how it minimizes unnecessary disk I/O and why that architectural decision plays such an important role in delivering high performance analytics at Exasol. Let's get started. Yeah, so let's get started of episode 4 of Know Exasol, where we will discuss about how Exasol is using its main memory. So, why disk is the enemy of analytical speed? Why I'm telling that? Traditional databases were designed for a different class of workloads. As we discussed in the first episode, there are two different workloads. One is OLTP, the transactional based, another one is analytical based, OLAP. For a transactional systems, reading and writing relatively small amounts of data from disk is perfectly acceptable. But analytics is different. A single query may need to scan millions or even billions of records. When every query repeatedly reads data from disk, the storage throughput and disk latency quickly become the limiting factor. I hope you all agree with that. So Exasol takes a different approach. So what is that approach? It is Exasol's memory first approach. Rather than relying on disk for active processing, it minimizes disk I/O by processing data locally in main memory whenever possible. So the disk remains important for persistence and durability, but analytical execution is designed around memory. So Exasol's node level data layers. Let's look at the architecture inside the node. According to the Exasol documentation, data is distributed across all nodes in the cluster, and most data is processed locally in the main memory of each individual node. So at the highest level, we can think of three important components. First is main memory, where active query processing happens. Then we have a main segment, which provides durable and disk persistence for the node's data. So finally, secondary segment. Secondary segments provide mirrored copies that support high availability and recovery scenarios. So this combination, main memory, main segment and secondary segment, allows Exasol to deliver both high performance execution and resilient data storage. So now let's see what happens when a query arrives, warm data versus cold data. The receiving node distributes the query across the cluster. So each participating node first check whether the required data is already available in the main memory. Nothing but a cache kind of a thing. If it is, the query can continue immediately with minimal disk access. If the required data is not currently resident in memory, only the required columnar segment are loaded from disk. The actual filtering, joining, and aggregation operations then happen in memory. Another important optimization is that Exasol only loads the columns required by the query rather than the entire rows, which we already saw the columnar storage. How does it work? And instead of reading entire workload, it takes only the columnar things whichever is required based on the query, which we already seen. So the combination of columnar storage and in-memory processing significantly reduces unnecessary I/O. So how Exasol fits more into RAM? Columnar storage offers another major advantage, which is efficient compression. Imagine a column containing millions of rows with the same country value. Rather than repeatedly storing identical values row after row, column oriented storage enables high efficient compression techniques. The result is that much more data can fit into available memory. More data stays warm. Less data needs to be transferred. So less data need to be scanned. And analytical queries can execute much more efficiently. Importantly, this optimization are handled automatically by Exasol without requiring manual tuning from the user. So what in-memory processing delivers? The architectural benefits become very clear when viewed together because analytical execution primarily happens in main memory. Exasol can significantly reduce unnecessary disk I/O during query execution. As additional nodes were added to the cluster, both CPU resources and available memory increase. That allows the platform to scale larger analytical workloads while maintaining efficient distributed execution. Keeping frequently accessed data in memory also helps support high concurrency analytical workloads with more predictable performance characteristics. So, let's discuss in-memory versus disk side by side. The difference between these two approaches is architecturally rather than incremental. In traditional disk-oriented system, repeated storage access can become the primary bottleneck. In Exasol, frequently accessed data can be processed directly from the main memory, significantly reducing dependence on disk during analytical execution. Combined with custom columnar compression and distributed processing, this architecture enables fast and efficient execution across a large data sets which is being used in analytical workloads. It's multiple architectural decisions working together which makes Exasol better performance analytical engine. So what is the key takeaway? So at this point in this series, we covered several important building blocks behind Exasol's analytical performance. Columnar storage reduces unnecessary data access. In-memory processing minimizes unnecessary data I/O. Massively parallel processing distributes data across all nodes. Share nothing architecture removes centralized bottlenecks. These are all isolated features. Together, they form the architectural foundation of the Exasol's analytical engine. In the next episode, we will move one level deeper and look inside Exasol's analytical execution engine to understand how distributed query processing actually happens across the cluster. Thanks for joining. Let's connect in next episode. Thank you.